Today's topic is ultraviolet and visible spectroscopy from organic chemistry. Electromagnetic radiations. Visible light is a form of energy which can be described by two complementary theories, that is, corpuscle theory and wave theory. Neither of these theories can explain all the properties of light. Some properties of light, such as photochemical effect, blackbody radiations, can be explained only by corpuscle theory, while the other properties of light, such as diffraction, interference, etc., can be explained only by the wave theory. Next is electromagnetic wave theory. Wave theory was put forward by James Maxwell in 1864. According to this theory, first, energy is emitted from any source continuously in the form of waves or radiations, and the energy thus emitted is called radiant energy. The most common example of radiant energy is heat, light, X-rays, etc. Second, each radiation consists of mutually perpendicular oscillating electric and magnetic fields, both of which are perpendicular to the direction of propagation of the radiation. Third, all the radiation have wave character and travel with the velocity of light, that is 3 into 10 to the power 10. Electromagnetic spectrum. The field of spectroscopy deals with the study of absorption or emission of electromagnetic radiations. We are familiar with a number of different types of electromagnetic radiation, such as cosmic rays, X-rays, ultraviolet light, visible light, infrared radiations, radio waves, radar waves, etc. All the electromagnetic radiations travel with the same velocity, that is 3 into 10 to the power 10 centimeter per second, but differ from one another in the wavelength of their waves. The arrangement of all types of electromagnetic radiations in the order of their increasing wavelength or decreasing frequency is called the electromagnetic spectrum. Next is spectroscopy is the study of interaction between matter and electromagnetic radiation, radiant energy that displays the property of both particles and wave. Several different photometric techniques are used to identify compounds. Each employs different types of electromagnetic radiations. We will start here by looking ultraviolet and visible spectroscopy. UV and visible spectroscopy provides information about compounds with conjugated double bonds. Ultraviolet light and visible light have just the right energy to cause an electronic transition, the promotion of an electron from one orbital to another of higher energy. Depending on the energy needed for the electronic transition, a molecule will absorb either ultraviolet or visible light. If it absorbs ultraviolet light, a UV spectrum is obtained. If it absorbs visible light, a visible spectrum is obtained. Ultraviolet light is electromagnetic radiation with wavelength ranging from 180 to 400 nanometer. Visible light has wavelength ranging from 400 to 780 nanometer. Wavelength is inversely related to the energy. The shorter the wavelength, the greater is the energy. Ultraviolet light therefore has greater energy than visible light. We know E is equal to hc by lambda, where h is equal to Planck's constant, c is equal to velocity of light, and lambda is equal to wavelength. The normal electronic configuration of a molecule at its ground state, all the electrons are in the lowest energy molecular orbital when a molecule absorbs light of an appropriate wavelength and an electron is promoted to an higher energy orbital. The molecule is then in an excited state. Thus, an electronic transition is the promotion of an electron to a higher energy molecular orbital. The relative energies of the bonding, non-bonding and anti-bonding molecular orbitals are shown. Ultraviolet and visible light have sufficient energy to cause only the two electronic transitions. The electronic transition with the lowest energy is the promotion of a non-bonding electron into an anti-bonding molecular orbital. This is called an N to N star transition. The higher energy electronic transition is the promotion of an electron from a bonding molecular orbital into an anti-bonding molecular orbital. This means that only organic compounds with electron can produce UV visible spectra. Principles of UV spectroscopy. Whenever UV radiation is passed through the solution of an organic compound, it is either absorbed or transmitted depending upon the wavelength and its molecular structure of the organic compound. As a result of the absorption of the energy, an electron gets excited from the electronic state to some higher electronic state. During this absorption process, some of the molecules of the organic compound will collide with the photons of the radiant energy. Although a large number of such photon molecule collisions are possible, but only those will result in absorption of energy in which the energy of the photon exactly matches the difference in energies of the electron in the ground and the excited electronic states of the molecule. If E0 and E1 are the energies of the ground and the first excited state energy, then electronic difference or energy difference is equal to E1 minus E0. The Beard-Lambert law. Wilhelm Beer and John Lambert independently proposed that at a given wavelength, the absorption of a sample depends on the amount of absorbing species that the light encounters as it passes through a solution of the sample. In other words, absorbance depends on both the concentration of the sample and the length of the light path through the sample. The relationship among absorbance, concentration and the length of the light path is known as the Beer-Lambert law and is given by A is equal to epsilon Cl, where A is equal to absorbance of the sample, I0 is equal to intensity of the radiation entering the sample, I is equal to intensity of the radiation emerging from the sample, C is equal to concentration of the sample in moles per liter, L is equal to length of the light path through the sample in centimeters, and epsilon is the molar absorptivity. Molar absorptivity. The molar absorptivity of a compound constant that is a characteristic of the compound at a particular wavelength. It is the absorbance that would be observed for a 1 molar solution in a cell with 1 cm path length. The molar absorptivity of acetone, for example, is 9000 at 195 nanometer and 13.6 at 274 nanometer. The solvent in which the sample is dissolved when the spectrum is taken is reported because molar absorptivity is not exactly the same in all solvent. So the UV spectrum of acetone in hexane would be reported as 195 nanometer, 274 nanometer because absorbance is proportional to concentration. The concentration of a solution can be determined if the absorbance and molar absorptivity at a particular wavelength are known. Epsilon is equal to E by Cl. Presentation of spectra. The ultraviolet visible spectrum is generally recorded as a plot of absorbance versus wavelength. It is customary to then plot the data with either E or log E plotted on the ordinate and wavelength plotted on the abscissa. The spectrum of benzoic acid is typical of the manner in which spectra are displayed. However, very few electronic spectra are reproduced in the scientific literature. Most are described by indications of the wavelength maxima and absorptivities of the principal absorption peak. For benzoic acid, a typical description might be as shown in the figure. Next is solvents. The choice of the solvent to be used in an ultraviolet spectroscopy is quite important. The first criteria for a good solvent is that it should not absorb ultraviolet radiation in the same region as the substance or spectrum is being determined. Usually, solvents that do not contain conjugated system are most suitable for this purpose, although they vary regarding the shortest wavelength at which they remain transparent to ultraviolet radiation. Table 7.1 lists some common ultraviolet spectroscopy solvents and their cutoff points or minimum regions of transparency. Of the solvent listed in table, water, 95% ethanol, and hexane are most commonly used. Each is transparent in the regions of the ultraviolet spectrum in which interesting absorption peaks from sample molecules are likely to occur. A second criteria for a good solvent is its effect on the fine structure of an absorption band. Figure 7.5 illustrates the effect of polar and nonpolar solvents on an absorption band. A nonpolar solvent does not form hydrogen bond with the solute, and the spectrum of the solute closely approximates the spectrum that would be produced in the gaseous state, in which fine structure is often observed. In a polar solvent, the hydrogen bonding forms a solute-solvent complex and the fine structure may disappear. Types of electronic transitions. The absorption of electronic transition by organic compounds in the UV and visible region occurs due to extension of electron from bonding or non-bonding molecular orbital to antibonding molecular orbital, which are usually vacant in the ground state of the molecule. The electronic transitions that occur in UV and visible region are of the following type. First transition, that is from sigma to sigma star. Transition in which an electron is excited from sigma bonding molecular orbital to sigma star antibonding molecular orbital are called sigma to sigma star transition. These transitions are shown by only those compounds in which all the electrons are involved in sigma bond formation, that is in saturated hydrocarbons. These requires very high energy. Therefore, these transitions occur at short wavelength or high frequency and are usually found in vacuum or far ultraviolet region. For example, methane absorbs at 125 nanometer and propane at 135 nanometer. Second is N to sigma star. Transition in which a non-bonding electron is excited to sigma star anti-bonding molecular orbital are called N to sigma star transition. These transitions occur in those compounds which contain heteroatoms such as oxygen, nitrogen, sulfur, halogens, etc. For example, alcohol, ethers, alkyl halides, amines, aldehyde and ketone show this type of transition. This transition requires lower energy than sigma to sigma star transition and hence occur at longer wavelength than sigma to sigma star transition. In fact, the energy required for these transitions depend upon the electronegativity of the heteroatom. Lower the electronegativity, higher the wavelength of absorption. For example, methyl alcohol absorbs at lambda max at 258. Third is pi to pi star transition. Transitions in which a pi electron is excited to an anti-bonding orbital pi star molecular orbital are called pi to pi star transition. This type of transition occurs in saturated compounds containing double bonds and also in aromatic compounds. These transitions generally require a large amount of energy and hence occur at short wavelength. For example, organic compounds containing isolated unsaturated center, the absorption due to pi to pi star transition occurs well outside the range of ordinary spectrophotometers. In saturated aldehydes and ketone, the pi to pi star transitions produces an absorption band of high intensity at about 285 nanometer. Fourth is N to pi star transition. Transition in which an electron is excited from the non-bonding atomic orbital to the pi star molecular orbital are called N to pi star transitions. All organic compounds containing a double bond between carbon and some heteroatoms such as carbon oxygen, carbon sulfur, nitrogen oxygen, etc. Shows this type of transition. The effect of conjugation. One of the best ways to bring about a bathochromic shift is to increase the extent of conjugation in a double bonded system. In the presence of conjugated double bonds, the electronic energy levels of a chromophore move closer together. As a result, the energy required to produce a transition from an occupied electronic level energy level to an unoccupied level decreases, and the wavelength of the light absorbed becomes larger. So the figure illustrates the bathochromic shift that is observed in a series of conjugated polyenes as the length of the conjugated chain is increased. The effect of conjugation on alkenes. The bathochromic shift that results from an increase in the length of a conjugated system implies that an increase in conjugation decreases the energy required for electronic excitation. This is true and can be explained most easily by the use of molecular orbital theory. According to MO theory, the atomic p orbitals on each of the carbon atom combine to make p molecular orbitals. For instance, in case of ethylene, we have two atomic p orbitals, F1 and F2. From these two p orbitals, we form two p molecular orbital Y1 and Y2 dash. By taking linear combinations, the bonding orbital Y1 results from the addition of the wave function of the 2p orbital, and the anti-bonding orbital Y2 star results from the subtraction of these two wave functions. The new bonding orbital has an energy lower than that of either of the original p orbitals. Likewise, the anti-bonding orbital has an elevated energy. Chromophoric group. The term chromophoric was originally applied to a system which imparts color to a compound. For example, nitro group is a chromophore since it imparts yellow color to a compound. Similarly, aryl conjugated azo group is a chromophore since it imparts color to the azo dyes. But now the term chromophore is used in a much broader sense. Thus, a chromophore is now defined as any functional group that absorbs electromagnetic radiations irrespective of the fact whether it imparts color to the compound or not. For example, a carbonyl group is a chromophore since it absorbs in the UV region at around 279 nanometer with a molecular excitation coefficient of about 15. Chromophores such as carbon double bonds and carbon triple bonds which contain pi electron and hence undergo pi to pi star transitions. Chromophores such as carbonyl, nitrogen, NO2 which contain both pi and n electron and hence undergo pi to pi star and n to pi star transition. Auxochromes. Groups which themselves do not show any characteristic absorption above 200 nanometer but which when attached to a given chromophore usually cause a shift of absorption band to longer wavelength with a simultaneous increase in the intensity of the absorption band are called auxochromes. Some common examples of auxochromic groups are hydroxyl, sulfhydryl and their derivatives such as OR, NHR, NR2, SR, etc. and some of the halogen. For illustration, consider the following compound, that is trans-azobenzene and trans-p-ethoxyazobenzene. Trans-azobenzene absorbs at 320 nanometer with epsilon max 21,000. However, the presence of an auxochrome such as ethoxy group at the para position shift the lambda max to 385 nanometer with the intensity. Benzene shows an absorption band at lambda max 254 nanometer with epsilon max of 230, but aniline shows lambda max at 280 nanometer with epsilon max of 1430. Thus, NH2 group acts as an auxochrome. However, the anilinium ion, which does not contain non-bonding electron, shows lambda max at 254 nanometer, which characteristics of the benzene ring. Bathochromic shift or redshift. The shift of absorption maxima to longer wavelength is called bathochromic shift or the redshift. This can be achieved by the following three ways. First, by attaching an oxochrome to the carbon-carbon double bond or the benzene ring. As discussed above, placement of an oxochrome such as ethoxy group at para position of trans-isobenzene shifts its longest wavelength absorption band by 65 nanometer to longer wavelength and also increases its intensity twofold, that is trans-p ethoxyisobenzene, where lambda max is equal to 385 nanometer. Second, by conjugation of two chromophores. For example, ethylene absorbs strongly at 175 nanometer in the far UV region, but when two double bonds are brought in conjugation, just as in butadiene, the pi to pi star transition undergoes a bathochromic shift with hyperchromic shift and butadiene absorbs at 2701 nanometer. Third is by decreasing the polarity of the solvent. For example, acetone shows a lambda max at 264.5 nanometer water due to N to pi star excitation. If hexane is used as a solvent, the absorption maximum shifts to 279 nanometer. Second is a hypsochromic shift. A shift of absorption maxima to shorter wavelength is called hypsochromic shift or the blue shift. This may caused by the following factor. First, by attaching an oxochrome to the carbonyl group, for example, N2 pi star transition of acetaldehyde appears at 293 nanometer, but it undergoes a hypsochromic shift when its hydrogen atom is substituted by an oxochrome. Second is by increasing the polarity of the solvent. For example, N2 pi star transition of acetone in hexane appears at 279 nanometer, but this absorption shift lower wavelength and appears at 264.5 nanometer in water. As already explained, this blue shift is due to hydrogen bonding which lower the energy of the electron, thereby increasing the energy gap between the N and pi star orbitals. Third is hyperchromic shift. This effect leads to an increase in molarity absorptivity. Further, bathochromic effect is often accompanied by hyperchromic effect. For example, when phenol is converted into phenoxyethanol, both the primary and secondary bands of phenol shows a bathochromic shift with hyperchromic effect. Hypochromic effect. This effect leads to a decrease in molar absorptivity. Further, hypsochromic shifts are often accompanied by hypochromic effect. Example, benzoic acid is converted into benzoate ion or aniline is converted into anilinium ion. Both the primary and secondary band exhibit hypsochromic shift with hypochromic effect. Woodward-Fisher rules for calculation of lambda maximum of simple conjugated dienes. Woodward formulated certain empirical formula for calculating the lambda max for long wavelength pi to pi star transition for dienes and polyenes. These rules were later by Fisher in 1959. According to these rules, each diene has a certain fixed base value and the value of the lambda max upon the following points. First, the alkyl substituent or ring residues present on the diene system. Second, the number of double bond extending conjugation beyond the diene system. Third, the presence of polar groups or oxochrome such as halides, OR, SR, NH2, OCOCH3, etc. For example, calculate the lambda maximum for the most intense band in the UV spectrum of 2,3-dimethyl 1,3-butadiene. So the structure of 2,3-dimethyl 1,3-butadiene is, it has 2 methyl substituent at position 2 and 3. Thus, the parent value for acyclic diene is 240 nanometer. 2 substituent is that is 2 into 5 is equal to 10 nanometer. Calculated lambda maximum is equal to 224 nanometer and the observed lambda maximum is equal to 226 nanometer. Next is Woodward-Fisher rules for calculation of lambda max for pi to pi star transition. Absorption band of alpha beta unsaturated carbonyl compound enones. Woodward and Fisher examined the UV spectra of a number of alpha beta unsaturated compounds in ethanol and formulated a set of empirical formula which help us to predict the lambda max of a pi to pi star transition in an unknown compound. These rules are summarized in below table. Solvent correction. Since pi to pi star absorption band is strongly affected by polarity of the solvent, therefore to convert lambda max values obtained in other solvents to standard ethanol solvent, the following correction has been proposed. For example, the solvent is methanol, correction is 0. For chloroform, it is +1, ether +7, hexane +8, cyclohexane +11, dioxane +5, water -8. Base values. Alpha beta unsaturated acyclic or 6-membered ring ketone 215 nanometer. Alpha beta unsaturated 5-membered ring ketone 202 nanometer. Alpha beta unsaturated aldehydes 207 nanometer. Alpha beta unsaturated esters 197 nanometer. Increments. Each alkyl group or ring residue 10 nanometer for alpha, 12 nanometer for beta, and 18 nanometer for gamma and higher. Each double bond extending conjugation 30 nanometer. Each exocyclic double bond 5 nanometer. Homoannular diene component 39 nanometer. That is two double bond which are conjugated with a carbon double bond oxygen group lie in the same ring. For example, calculate the lambda max for the following compound. So the given compound is an alpha beta unsaturated ketone having two alkyl substituent at beta position. So the basic value for the alpha beta unsaturated acyclic ketone is 215 nanometer. 2 alkyl substituent at beta position is equal to 24 nanometer. Therefore, calculated lambda max is equal to 239 nanometer and the observed value is 237 nanometer. Application for UV spectroscopy. Some important applications of UV spectroscopy are discussed below. First, detection of functional group. UV spectroscopy has been used to detect the presence or the absence of certain functional group in organic molecule. For example, in an organic compound does not show lambda max above 200 nanometer, it cannot contain a conjugated chromophore, that is carbon-carbon double bond, an aldehyde or a keto group or a benzene group. Second, detection impurities. Compounds with large lambda max can be detected when present as impurities even at a concentration provided the sample itself does not show any absorption in the impurities. Third is identification of geometrical isomers. UV spectroscopy can be used to distinguish between a pair of geometrical isomers. In general, trans compounds absorb at longer wavelength with higher extension coefficient than the corresponding cis isomers. Fourth, detection of formation of charge transfer complexes. UV spectroscopy is quite useful in detecting the formation of charge complexes as discussed below. Many electron-rich organic molecules such as mesitylene, aromatic hydrocarbon such as naphthalene, anthracene, etc., phenol and aromatic amines are to form charge transfer complexes with electronic deficient molecule such as aspartic acid, tetracyanoethylene, etc. Fifth is determination of extent of conjugation. One of the most important uses of UV spectroscopy is to detect and estimate the extent of conjugation in a polyene. Butadiene itself absorbs at 217 nanometer, but addition of each double bond shifts the absorption maxima to the longer wavelength by about 30 nanometer. Greater the number of such conjugated double bond, longer is the wavelength of absorption. Thank you.